Let's first try to realize a voltage controlled voltage source. Now, a voltage controlled voltage source has an output voltage which is some fixed constant times the input voltage. Okay, that is, let's say the input is applied between two nodes. There will be a voltage K times Vi, which is the output voltage. Okay. Now you may think that any linear circuit is like this, right? If you apply some input somewhere, then you will get an output which is some number times the input. That's the characteristic of a linear circuit. Okay. Any linear circuit will give you some K times the input. But there are other characteristics that are important for a voltage controlled voltage source. Okay. That is, you can connect an input voltage with any internal resistance. Okay. Now you can see that there is an open circuit between these two terminals, which are the controlling terminals of a voltage controlled voltage source. So this Vi appears here entirely. Okay. This is characterized by saying that the input resistance of a voltage controlled voltage source is infinity. Okay. If the input resistance is infinite, then you can use an imperfect source Vi with whatever value of Rs, but all of this input voltage appears across the controlling terminals of the voltage controlled voltage source. Okay, that's a very important thing. For instance, if you had a resistance here, Ri, then this voltage would not be Vi, but it would be Vi times Ri by Rs plus Ri. And if Ri is very small, the fraction of Vi that appears there could be very small also. Okay, Ri should ideally be infinity. In reality, it should be very, very large. Okay, so that for a range of values of Rs, the fraction of the input voltage that appears here is very close to 1. Okay. Similarly, you should be able to connect whatever load you want here. Okay, that shouldn't change the output voltage. What could possibly change the output voltage? It's output resistance. Okay, so let me call this Ro, that is the resistance looking back that way, the output resistance. Then you can see that, let's first imagine that Ri is infinity. So all of Vi appears here and this voltage source gives you K times Vi. But the actual output voltage that appears here is K times Vi times RL by Ro plus RL. Okay. So if Ro is comparable to RL or higher, then the voltage that you get across the load is very different from kVi. It is much smaller than that. So in reality, you can clearly see that Ro must be 0. So in this case, this fraction becomes 1. Okay. And similarly, Ri becoming infinity takes this fraction to 1. So that's the ideal characteristic of a voltage controlled voltage source. So the characteristic of a voltage controlled voltage source is that the input resistance Ri is infinity and the output resistance Ro is 0. Okay. In practice, we can't get an infinitely large input resistance. So Ri has to be very large. And when you have a quantity with dimensions like Ri, we have to say it is very large compared to what? And in this case, it should be much larger than the expected range of values of Rs. In that case, regardless of the value of Rs, this fraction here will be close to 1. Similarly, Ro, we cannot get it to be exactly 0. We want it to be very small. And what does very small mean? It should be much smaller than the expected range of values of RL. So again, if this condition is satisfied, this fraction here will be close to 1 and we will have a ratio of output voltage to input voltage which is K, which is also independent of Rs and RL. That is quite important. Okay. In a controlled source, the output quantity should also be independent of load resistance and source resistance. Okay. How do we realize this using a MOS transistor? First of all, because of certain restrictions, that is because the source is common to the control sites of the MOSFET, it turns out that we can only realize VCVS with K equals 1, that is V0 equals Vi. Okay, we'll come to this later. This is using a single MOS transistor. Now you can ask, what good is this? I already have the input voltage, why should I generate it again? The point is this one. We will generate a control source which will maintain K equal to 1 regardless of temperature and other process parameters that govern the transistor. And also we will maintain a very large input resistance and a very small output resistance. Okay, so such a circuit which doesn't provide gain, it provides unity gain, but still has input resistance tending to infinity and output resistance tending to 0. This is known as a voltage buffer. Okay, it still has its uses, because if you have Vi and some Rs and you have some RL, if you connect it directly, what you get here will not be Vi, it could be much smaller than Vi. Instead of that, if you connect it through a buffer, it has a gain of 1, but its input resistance is infinity and the output resistance is 0. In that case, the output voltage you can see is exactly equal to Vi. Okay, because at this point we'll get Vi and its output will get the same as the input. So here we'll get Vi and it's not affected by the value of RL. Okay, so what we'll be realizing is actually a voltage buffer. It's still quite a useful thing. It's also a very useful building block using a single transistor. Okay.